If I tell you, we have colliders that are 10 million times more powerful than the most powerful particle accelerator we have, would you believe it? This is not the plot of a science fiction movie. It's a shocking secret hidden in the moment of a star's death. When a supernova explodes, it doesn't just glow and heat. In just a few months, it can actually accelerate particles to the extreme energy that humans dream of. Why are most supernovae out of speed? Only a few can reach the end of the universe's acceleration. The answer lies in the final frantic struggle before the star dies. We all know that the Large Hadron Collider in Europe is the most powerful particle accelerator ever built. A terrifying energy that accelerates protons to 13 trillion electron volts. But on a cosmic scale, this number is simply dwarfed. The real ultimate collider in the universe is at energies of 100 trillion electron volts. This is equivalent to 100,000 times the LHC energy. Scientists call this superaccelerator PEV quasi. They're like invisible behemoths of the universe, secretly producing the highest energy cosmic rays. But less well known is finding these PEVs is harder than finding a needle in a haystack. For a long time, astronomers have long suspected that supernova remnants in the Milky Way are the true nature of these mysterious accelerators. After all, when a massive star explodes violently at the end of its life, the resulting shockwave has unparalleled energy. It seems to be fully capable of pushing particles towards their ultimate speed. However, reality has given scientists a resounding slap in the face. In recent years, young supernova remnants have been observed by radio telescopes, X-ray satellites, and gamma-ray detectors. For example, the famous Emperor Valley supernova remnant and Cassiopeia shows a puzzling phenomenon. They do accelerate particles, but the highest energy is stuck around 100 trillion electron volts. It has never been possible to break through the critical threshold of PEV. It's like a supercar that was supposed to go 300 kilometers an hour. However, he could not break the speed limit of 30 kilometers per hour. What's stopping supernova from doing their real work? To understand this mystery, we must first understand what cosmic rays are. Cosmic rays are streams of high-energy particles from outer space. They hit the Earth's atmosphere at nearly the speed of light. The highest energy particles are even millions of times stronger than those produced by LHC. Where do these superenergetic particles come from? This question has puzzled astronomers for a century. The most promising candidate is the massive shockwave structure left behind by the explosion of the supernova remnant star. Well, in theory, these shockwaves are like particle runways in the universe. It can be accelerated by a mechanism called Fermi acceleration. Accelerate the particles to higher energies again and again. But the actual observation is surprising. In 2021, observations from the High-Altitude Cosmic Ray Observatory and the High-Altitude Water Vapor Length Gamma Ray Observatory confirmed that there are indeed several PEV quasi-class particle accelerators in the Milky Way. But here's the thing. The exact identities of these cosmic behemoths remain a mystery, and the most promising young supernova are involved. However, it has never been able to achieve the acceleration ability of the PEV. It's like you're looking for a hidden superhero. All the clues point to someone, but when you actually find him, however, he found that his ability was far from as powerful as the legend said. What's the problem? The traditional supernova model assumes the blast wave travels through the relatively smooth and thin interstellar space, like a stone thrown into a calm lake. Generate neat circles of ripples. In this perfect environment, shockwaves do accelerate particles, but the acceleration efficiency is limited. However, the real universe is much more complex than theoretical models. Recent studies have found that the problem is not the explosion itself. It's in the environment around the star before it exploded. In the final stages of the life of a massive star, they go through a period of intense deathbed struggles. These dying superstars, in particular, blue variables and red supergiants, it would eject huge amounts of material in a frenzy in the months 2 years before the core collapsed. The ejected material is not evenly distributed in space. Instead, it forms a dense shell of material. It was as if the stars had wrapped themselves in a thick armor. When the shock wave of a supernova explosion hits these dense shells, the real miracle began to happen. In 2025, an international team, led by the Max Planck Institute for Physics in Germany, published a paper in the Journal of Astrophysics and Astronomy. Breakthrough research published in, they did very sophisticated numerical simulations. For the first time, it completely recreates the whole process of how a supernova transforms into the ultimate impact of the universe. The core finding of this study is quite striking. Only under extremely specific conditions, only supernova can exert their true peering acceleration ability. The key to this process lies in the dense shell of material formed before the explosion. In the last year or two of a massive star's life, it goes through an extremely unstable nuclear fusion process, like a pressure cooker about to explode. Violent reactions inside stars can cause violent eruptions of surface material. In just a few months, stars may eject material equivalent to 1 or 2 solar masses, forming a dense crust that is 1,000 to 10,000 times denser than normal interstellar space. The key feature of this shell is that it has to be very close to the star's surface, only 3,000 to 30,000 astronomical units from the center of the star. This is equivalent to putting a body armor on the star. When a star's core collapses, it causes a supernova explosion. The resulting shock waves travel outward at tens of thousands of kilometers per second. Under normal circumstances, the shock wave gradually loses its energy in the thin interstellar space. It was like a ball rolling on the beach gradually coming to a stop. But when the shock wave hits the dense material, it's completely different now. It was like a cannonball hitting a steel plate. Huge resistance not only won't stop the shock wave, instead, it generates even more intense turbulence and magnetic fields. The research team used advanced computer code called RAT. The detailed process of the interaction between the shock wave and the dense shell is simulated. They discovered that, as the shock wave passes through a dense area, it triggers a physical phenomenon called the Bell instability. This instability is like an amplifier for a magnetic field. It can enhance the originally weak magnetic field dozens of times. The existence of a strong magnetic field is the key to particle acceleration. They're like invisible runway railings, prevent high-energy particles from escaping the acceleration zone. At the same time, it provides stronger acceleration. Under the combined action of a strong magnetic field and severe turbulence, particles trapped in the shockwave begin to experience a frenetic acceleration process. Every time a particle passes repeatedly before and after the shockwave, we'll get extra energy. It was like a pinball bouncing back and forth between two moving walls. It's getting faster and faster. The simulation results show that, under ideal conditions, the maximum energy of a particle can jump from 1 trillion electron volts to 100 trillion electron volts in just a few months. It's an incredible triple jump. But there's a critical time window in which this superacceleration lasts only about 5 months. The research team's most significant discovery was a supernova transformation. The process of PeV positive is extremely short. It's like a flash in the pan. When a supernova shockwave first passes through the dense crust of the jinglet, intense interactions can increase the intensity of the magnetic mass flow by several dozen times over a period of months. It's like suddenly adding super horsepower to a particle accelerator. The maximum energy of the particles rapidly reaches the peak level of 1 to 3 price-to-earnings ratio 4. As the shockwave continues to expand outward, it's getting further and further away from the dense crust. The interaction gradually weakens. The strong magnetic field begins to decay. The efficiency of particle acceleration decreases dramatically. In less than a year, the universe will eventually lose its PeV acceleration on impact, return to the mundane level of a few hundred terabytes. This discovery perfectly explains two mysteries that have long puzzled astronomers. Why are only a few supernova able to achieve PE level? Because the excitation conditions are extremely harsh. Only those that experience violent eruptions of material before the eruption form supernova in close proximity to a dense crust, to have the potential to transform into a PE level. The vast majority of ordinary supernova do not possess this special equipment. Why is it so difficult for observations to capture the PeV accuracy? Because supernova have very short PR. When we look with telescopes at the remnants of supernova that are hundreds or even thousands of years old, they have long since missed the most glorious spring period. It's like trying to find a singer in an empty stadium after a concert. It would be as if there was a rare supercar in the universe. It performs at its best only under certain conditions, and this state can only last for a few months. When we finally found these sports cars, most of them have returned to normal driving conditions. Since the supernova pay is so short, how can we catch these cosmic lightning bolts? The research team has provided clear guidelines for future observations. They targeted an N-type supernova, type being supernova, or a special type of supernova. They show very strong hydrogen lines in their spectrum. It shows that the blast shockwave is interacting violently with hydrogen-rich dense matter. This is the ideal condition for forming a pay criteria. These supernova are usually brighter than normal supernova. It lasts longer. Like a super searchlight in the sky, it provides us with important clues for identification. Now, of course, timing is critical. The observation window is extremely limited. Astronomers must focus all their efforts on high-energy gamma-ray observations during the first 12 months after a supernova explosion. Missing this time window is equivalent to missing the best opportunity to observe the PEV. The research team suggests that, it requires combined X-ray, gamma-ray, and radio observations. form an all-round monitoring network. In particular, pay attention to detecting gamma ray flickers at the PeV level of TV. This is the most direct evidence of PeV activity. Next-generation high-energy astrophysics facilities, such as the upcoming Cherenkov telescope array and the improved LASER, it will provide us with unprecedented observation capabilities. They're like astronomers armed with super night vision goggles, capable of capturing the faintest high-energy signals in the darkness of the universe. And here's the interesting thing. This study of pure astrophysics has also shed light on particle physics. The natural particle energies in the universe can produce much higher particle energies than any man-made accelerator on Earth. This provides a unique laboratory for studying physical phenomena at extremely high energies. Although we cannot recreate the extreme conditions of supernova on Earth, but by looking at these natural cosmic pairs of impacts, we may be able to uncover new physical phenomena that will never be observed in a laboratory on Earth. As we gaze at the seemingly calm stars in the night sky, it's hard to imagine them becoming such powerful particle accelerators at the end of their lives. It's even harder to imagine this extreme physical process can be so short. In 13.80 billion years of cosmic history, each P means that the standard active period is only a few months. It's like searching for a fleeting flash of lightning in an eternal universe. But it's these short-lived extreme events that drive the evolution of the universe. Produces the highest energy cosmic rays. It shapes the fabric of space and time around us. Perhaps this is the most fascinating part of the universe. In seemingly infinite time and space, hidden are countless short-lived but amazing miracles. As the famous astrophysicist Carl Sagan once said, the universe is not only more wonderful than we think, it's more amazing than we can imagine.